Hi, welcome back to 5 Minute Physics. Let me begin by reading a quote from Richard Feynman's Nobel speech. He said, "It's always seemed odd to me that the fundamental laws of physics, when discovered, can appear in so many different forms that are not apparently identical at first. But with a little mathematical fiddling, you can show the relationship. It was something I learned from experience. There's always another way to say the same thing that doesn't look at all like the way you said it before. I think it's somehow a representation of the simplicity of nature. I don't know what it means that nature chooses these curious forms, but maybe that is a way of defining simplicity. Perhaps a thing is simple if you can describe it fully in several different ways without immediately knowing that you are describing the same thing." So this harkens back to simplicity, as I talked about earlier. And I want to use that idea to take what is probably one of the most boring things in physics and turn it into one of the most interesting things in physics. And I want to begin with that boring thing, which is called Snell's Law, something so boring that I sometimes didn't even include it in introductory physics classes, because I just said the students could memorize the equations on their own, because that's all the students ever ended up doing. Snell's Law was discovered by Willibrord Snell in, I think, 1621. He never actually published it, but for some reason he gets credit for it, it was a different world back then. And it basically says if light is going between a more dense medium and a less dense medium, and that usually means in our modern language, we say the index of refraction is much bigger than 1 here, and the index of refraction is about equal to 1 there, but it doesn't really matter. It's more dense versus less dense. Then the light will bend. It will refract. And so the light's moving this way. And if this is the angle theta 1, and this is the angle theta 2, then if it goes from a more dense to a less dense medium, then this angle will always be bigger than that angle. Namely, the light ray will bend outwards if it goes from a more dense to a less dense medium. And if I were to reverse these arrows, it would bend inwards if it was going from a less dense medium to a more dense medium. And there's a relationship between the sine of these angles and the index of refraction, and that's the formula that physics students or some students memorize, and it's boring. Now, this actually was kind of relevant in one way, in the sense that it was part of what was used to sort of prove that light was a wave, because you can show that if you had a particle that was going from a less dense medium to a more dense medium, then it would bend the opposite direction. Basically, if you had a particle coming in here, it would experience more resistance, and it would bend outwards instead of inwards, whereas a wave bends that way. And the key thing about this is that the wave is traveling faster in the less dense medium than the more dense medium. And that's what's important, that the wave speeds up when it goes from here to here, and light speeds up when it goes to a less dense medium and it bends outwards. Now, there's one other little bit. If you think about this, if it bends outwards, eventually you're going to get to an incoming angle, where this bending outwards is going to be horizontal or even more. And at that point, what happens for any angle greater than that angle, theta primed, then in fact, if light impacts on this medium for any angle greater than that, it will actually reflect. So if the grazing angle is very large, if this angle is very large so that the light ray is coming in almost parallel to that surface, it will reflect. So those are the properties of Snell's law, and that's it. Okay, great. And that describes refraction, and opticians use it all the time to design lenses to help people see. But it's not very interesting. But 40 years after Willibrord Snell did this, Pierre de Fermat, who was a mathematician, he was actually a lawyer turned mathematician, which shows that there's hope for everyone. He's famous, of course, for having claimed that of course the famous law x squared plus y squared equals z squared, which works for right triangles on a flat plane, doesn't have any solutions if for x to the n plus y to the n equals z to the n for any integers. That was his famous, for n greater than 2. And that was a famous theorem of Fermat that took 300 years to prove. That's why we remember his name. But actually, he showed something else that I find is much more interesting and will be useful in the next few days. He said that there's a completely equivalent way of understanding Snell's law, and it's weird. He said that you can understand, you can derive the path that light will take to go from any 2 points, A to B, under the assumption that light takes the least time to go from there to there. So light will take whatever path takes the least time. Now, you might say that's crazy because, of course, from A to B, the least time will be just a straight line. Light would always travel in a straight line, but that's not the case. Because remember, light is traveling more slowly in this more dense medium here than it is there. And if light takes this straight line, it goes this far in the more dense medium. Whereas if it takes this line, it only travels that far in the more dense medium. And since it's going more slowly in the more dense medium, you can show that, in fact, the travel time from there to there will be longer if it takes a straight line than if it goes on this bent path. Similarly, you could say, well, let's spend as little as possible time in the more dense medium and go almost straight down, but then you have more distance in the less dense medium, and once again you can calculate that the time traveled is longer. And if you work it out, the path that takes the least time is for the light to travel from here to here and then bend from here to here. So Snell's law comes from something that is completely different. It's derived exactly and mathematically equivalently by showing that light will take the path that takes the least time. It's like somehow light figures out, looks around and how am I going to get there fastest, and takes that path. Of course, it doesn't have intentionality, but it acts like it has intentionality, perhaps another point relevant for nature. So this principle of least time is fascinating to me, and it was actually fascinating to Feynman too, because it gives a totally different picture that derives the same result. Now, we can use that principle of least time and extend it, and we'll do that tomorrow. But the principle of least time allows us to describe things that we normally see in different ways in a very exciting way, I think. And one of those ways is a mirage. Many of us have experienced mirages if we're driving in a car on a very hot day and we're looking down the road and we see the sun and sky. It looks like there's a wet patch, but when we get there, there's no wet patch. Of course, it's famous for people in the desert seeing mirages and thinking that they're oases, but most of us haven't been stranded in the desert. More of us have been driving on a highway and seen them. What happens here? So here's the sun, and here's your eye, and of course the sun, you can look out directly and see the sun and see the light ray coming here. But then another way the light ray can get to your eye is by coming down here, and now this is the hot surface of the road, and the hot surface heats up the air around it. So the air in this first layer is hotter than the air in the second layer, which is hotter than the air in the third layer, which is hotter than the air in the fourth layer. Now, hot air is less dense than cold air. So when the light ray comes in here, it goes from colder air to warmer air, and that's more dense to less dense, so it bends outward. And then it follows down here, and it goes to another region which is from more dense to less dense, and it bends outwards. And then it does the same thing here, but now the grazing angle is so small that it does total internal reflection, so it goes up here, and then of course it bends the opposite direction, and then bends the opposite direction, and I should have put my eye right here. I didn't do that very well, but you get the point. Light can, by continuing to refract, it can eventually come up to our eye here. And that's the normal explanation of a mirage. The light from the sun comes down and refracts on a very hot day through many layers of air and keeps refracting until it totally internally reflects and then comes up to your eye. Okay. But of course, what we can do with this, with Fermat's theorem of least time, is say, what does the light do? Well, it can come straight to your eye, which is one way, and it can. But a way where it can also travel and take the least time is for it to decide, look, you know what? The air is a lot less dense down here. I'm going to spend more time down there, and then spend less time up here and come to your eye. And we can, of course, it'll take the same path as I drew there, but I just drew this for illustration. And so we can understand a mirage as light saying, I want to get to your eye, but I want to take the time that takes shortest, and I'm going to spend as much time as I can down there and come up to your eye. Again, of course, that's not what light does, but it acts like it does. And that idea that something like light follows a principle, a least time principle, suggests something perhaps more basic and more fundamental about nature, which we'll follow up on tomorrow. But let me just end today by saying, by quoting another statement from Feynman in his Nobel Prize lecture. He said, theories of the known, which are described by different physical ideas, may be equivalent in all their predictions and hence scientifically indistinguishable. However, they are not psychologically identical when trying to move from the basic to the unknown. For different views suggest different kinds of modifications which might be made and hence are not equivalent in the hypotheses one generates from them in one's attempt to understand what is not yet understood. So what he said is, you should try many different ways of understanding something if you want to move beyond to understand the unknown. Well, that's true at the forefront of science, but it's true for all of us learning physics. If you look at something and don't understand it one way, sometimes picturing it another way, another explanation that's equivalent, will resonate with you, and it's different for different people. So all of us respond to different explanations. Some of you may have liked Snell's Law as Snell defined it, but I like it much more with the principle of least time. And that will take us tomorrow to another fundamental principle in nature called the principle of least action, which will allow us to have a new picture of quantum mechanics. And by the way, I used a smaller piece of paper because some of you complained that I looked uncomfortable using a larger piece of paper. So talk to you tomorrow. Bye-bye.